color space in Hadron collisions is a lot more complicated than it was yesterday. The leading color approximation is much worse, and I'll discuss some of the phenomenology associated with that. I think we have a little bit more time to do that. So just to start with, of course, if you know parton distribution functions, again, they are these partitionings of the proton into a parton and a remnant, and we get information about what flavor that parton has and what momentum fraction it has. We do not get any information about what color it has. But okay, if it's a quark, it's a triplet, and then the remnant has to be an anti-triplet. And if it's a gluon, then it's an octet, and the remnant has to be an anti-octet. So there's 100% correlation. That's fine. We don't need the color when we pick out a single parton. But what about the next pattern that we pick out? What are the color correlations between the two patterns that we've picked out? If I picked out a quark and I pick out an anti-quark, are these two things going to be in a singlet with each other, or are they going to be in an octet and then leave the new remnant object in an octet as well? We don't have any information about that, right? So we can pick statistically, or we can make up some rules. And I'll just illustrate the ambiguity that we face when we pick out two parton from the proton. Here's a proton. I've divided it up into 3 valence quarks that are red, green, and blue. And then I've done 2 scattering processes here, and I've traced them in color space using this leading color, where a gluon is just the direct product of a color and an anti-color. So, you know, this gluon gets emitted by one of the quarks, that one gets emitted by another one of the quarks, then that quark scatters over here, blah, 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 blah. So I can talk about trace, if I wanted to, how the colors are going to go, and I've traced that over here, where I have a bit of a PT axis and a rapidity axis, where I have a diquark here. That's what we call the coherent superposition of combination of 2 quarks that are in an overall. These are 2 antiquarks. That's a p bar. This is tevatron. So that's going to be in an overall triplet. And that connects to, so I haven't disturbed those at all, right? That's just a diquark that goes down the beam pipe at very high rapidities. I haven't disturbed these 2, red, green, either. So they will just be a diquark going down the end, and there'll be a string between them. So that's this string here that is connecting these 2 in an overall blue state with these 2 in an overall anti-blue state. All the color that I've scattered into this event, I've taken off of, you know, one of the valence quarks, just saying that this was the active valence quark, and it emitted a gluon and then scattered or whatever. And then I can trace this blue color line will go to that quark there. That's this string between this one and that one, and so on. I can sort of trace again using leading color, where should the strings be going, and I can fragment that. And I can count the number of strings that I have per rapidity region. That should tell me basically my underlying event is not quite a plateau. It will be a plateau when I average over many events. But in this event, I will have 1 string in this region here down that beam pipe, then 2, then 3, then 4, then 2. So I'll have a sort of gradual a plateau with a number of steps in this particular event, if that was the color flow. But I didn't know whether that was this gluon here. I mean, maybe I should have attached it to one of the other valence quarks. If I just take that gluon down here, this red blue bar one, and move it down to the red quark, I don't know what I should do, right? Maybe I should sample randomly between that, or maybe once I've disturbed one's valence quark, it's more likely that that one emits again. We don't know. So if I just move it, what happens? I've done that, and some of the event topology doesn't change, some of it does. So now I can see that in this region here, if I just look at how many strings I've got, I've suddenly got 5 strings. I've disturbed more color. So somehow I'm scattering more color into the event. I would expect that now there's more strings, because I'm not using the same quark twice. And then in this beam region, now I've disturbed all the valence quarks. So this little diquark from before doesn't hang together anymore. It's now stretching strings to 3 different places. And there's something funny here, where a red, green, blue string is coming together. And I've scattered the baryon number into the event. This is called a string junction, and I'll maybe talk about them a little bit more later on, but it's a different kind of string topology that has a red, green, and a blue leg, and it carries baryon number. So there's going to be a baryon number hanging out, a baryon hanging out here in this part of the phase space. So a priori, this is totally just an ambiguity. I don't really know. Nothing fundamental is telling me what to do here. So I have to make up a rule for how often should I do which option. Yes? It's not a baryon yet. It's just that I have topology where three strings are meeting. When those strings fragment, a baryon is going to form around that. So it's not a baryon yet, but there will be a baryon forming around that junction. Right, so different models make different ansatz, but you can already see here there's an ambiguity that was not there in E plus E minus collisions, where we don't know how to correlate all these multi-parton interactions. They all have initiator partons that are coming from a remnant, and we don't know what their mutual color correlations should be. We have to make an ansatz about it. Then we have all these multi-parton interactions scattering out into phase space, and we last time we discussed this leading color approximation was equivalent to letting the number of colors go to infinity. So we're scattering all these colors and we're saying, oh, they're all different. Color line 101, 102, 103. So we have a picture where, all of these strings are different colors. But they're all being scattered from the same beam, and sometimes they overlap in phase space. So do these systems really form and hadronize independently, or do we have some sort of notion of coherence where I've scattered a bunch of colors, but they actually realize that they are not independent, they are coherent superpositions, and maybe in the central region, I don't have 5 strings, but I have some smaller effective number of strings. Or do these strings somehow interact? If I thought of them as strings, there would be an incredibly high energy density here. If each one of them has 1 GeV per Fermi, then I'll add up 1, 2, 3, 4, 5, 6, 7. 7 GeV per Fermi now in this region here. Does that do anything? For instance, when we have heavy ion collisions, we know that when there's a very high energy density, it looks like we have something that they call a quark-gluon plasma. Is the string description going to break down if we put a lot of strings on top of each other? So there's lots of interesting questions here. So how do we hadronize hadron collisions when we have multi-parton interactions going on? In leading color, we would hadronize each multi-parton interaction independently of all others. So that's equivalent of this thing we called independent fragmentation in the first lecture. And we would have, that each of the partons would stretch strings to the beams. If each of these partons are gluons, then they stretch 2 strings, and so they would all be independent, and they would go like this. And I would have some regions in phase space, especially near the beams, where I have lots of strings that are sort of sitting on top of each other. And I would have all this crisscrossing stuff going on in the middle of the event. If I allow something called color reconnections, then I could rewire these strings and say, no, these are actually going to, this one will just see that there is an octet over there. There's an octet over there. So let me stretch a confining potential to that and a confining potential to that, if I can. And I'll sort of minimize the total potential energy, the total string length, the surface area, the world sheet area of the string topology that I'm creating, if there are rules that allow me to do that. That's generally called color reconnections. And I'll talk a little bit about that. One of the consequences is that between these jets, you can see that I'll actually create a boosted string piece. So I will have something like flow. All of these hadrons are going to start moving in a direction. It looks a little bit like what in heavy ion collisions they call flow. But this is just created by string boost effects. So once I add all of these things, we have hard interactions, showers, all of that. We have multi-parton interactions and their showers now as well. We get final state with very many colored partons. And so now we have to ask, who gets confined with whom? Do we have this simple leading color picture, or can we have color reconnections, or what? The most physical model for color reconnections is I think ours. That we came up with some years ago, but we had been thinking about color reconnections for many years. And it was an empirical thing that the data supported it and people were doing it, but we weren't quite sure what the rules were. And then we thought, well, you start from this leading color picture, which we know is an approximation. So we know we've thrown away some information in the leading color picture. And so you only know the leading color connections between all these partons. But then if you look at 2 random partons that are color disconnected according to leading color, they have nothing to do with each other in leading color, you could think about them as just uncorrelated in color space. Certainly if they come from 2 different MPI, they're probably uncorrelated to start with. And then just by the rules of SU3 algebra, you can say, well, if I have a random quark and a random antiquark, that are not color connected according to leading color, there should still be a 1 in 9 probability that they could be in a color singlet, which I would not see in leading color because I've thrown this away. And in the same way, I could take two quarks. There's also a coherent superposition of them where they can act in a diquark-like state, an anti-triplet, so red plus green, in an antisymmetric state, just by accident. And gluons, the same things. There's a 27 and some other things here. So we built a model based on those observations, just letting patterns that are not color connected in leading color, stochastically choosing color correlations. So we don't have a full color shower. We stochastically restore the missing information. So we think that that is at least motivated by the algebraic structure of SU. Then you have lots of different possibilities. So I've got quarks that are connected leading color, but they also have some other options available to them through this mechanism here. Which one are you going to choose? So now you have lots of different string topologies you could make. You have to have a selection principle. And of course, that's going to be the area law from string theory, that you want to pick the minimal space-time area of the topology that you make. So you minimize what we call the string length, but it's really the worldsheet area, the potential energy that we do in this. So we select the string topology that would have the minimal string length. So we think that that is possibly a good thing to do for these color reconnections, and it motivates them mathematically, physically. So they're not a completely arbitrary thing to do. So how do you confront models like this then with measurements? You would like to study things as a function of the number of color exchanges that you have, the number of multi-pattern interactions, but you can't measure that directly. For hard multi-pattern interactions, maybe you could measure the number of mini-jets, but that's also really tricky. So what we do in practice is we use the number of particles that are produced. How many tracks are you getting in the event? Is this a very busy event? Then there were probably many multi-pattern interactions. Or is it a very dilute event? Then there probably weren't that many. So we use the number of tracks as a rough indicator of how much color is getting kicked around in this event. And then we can study event properties as a function of the number of tracks. You may have seen lots of different things being plotted. It's a function of the number of tracks. So this is an example of two different tunes, baseline 50 and then Atlas AZ that they use for electric measurements in Atlas. And you can see that so here's the number of multi-pattern interactions, and you can see that these two different tunes, these two different models, this is the average number of generator level tracks over 4 pi that you produce in the events. They produce different number of charged tracks per multi-pattern interaction. But they both predict a very strong correlation between, so, like, am I going to use 2 multi-pattern interactions to create this number of tracks, or just 1 multi-pattern interaction? That's ambiguous. That depends on what the color reconnections are doing, and so how much am I reducing string length? So different models can have different correlations, or sorry, different sizes of this quantitatively, but they both predict a very strong correlation between what I can measure and the number of multi-pattern interactions. And that's what I really want. So this is an experimental observable. Yes, I do care what the slope is of these, but what I really care about is that there's a strong correlation between the quantities, no matter what the model is. So I can use the number of charged tracks as a proxy for the number of multi-pattern interactions. I cannot from that number infer how many multi-pattern interactions there were, but as I go from few to many in one quantity, I'm going from few to many in the other quantity as well. So consequences here is one of the early ones that we were looking at, that as I go in the number of charged particles in minimum bias collisions, I see that the average particle gets harder. So the average PT is rising as a function of the number of charged. So in busy events, each track has higher PT than in dilute events. If you don't have color reconnections, if I just have a bunch of independently hadronizing multi-pattern interactions, if I have one of them, it hadronizes, I get some particles with some spectra, and then I can overlay 5 of those on top of each other to get many particles, but I haven't changed the spectra of those particles. It's still just, just shooting 5 bullets instead of 1, but it has the same energy. But if I correlate them and I get these flow effects going with boosted string pieces, then some of the tracks are going to be having higher PT as I have more multi-pattern interactions. Each multi-pattern interaction is injecting more energy collectively into the event that is then giving these boost effects that make the tracks become harder. So that's an important observable that color reconnections were used to explain already from early on. There are also other interesting things that color reconnections can do. For instance, 3 quarks can randomly, with a small probability, but randomly, be in an overall color singlet. So I could reconfigure this string configuration into those string configurations. And then I could fragment them, and that's what we were talking about. There's no actual baryon here yet, but after the strings fragment, there will be a baryon forming around that little point, and we call that a junction baryon. Of course, they have to form in pairs. We're not violating baryon number. So there's a baryon and an antibaryon by color conservation. If I can do this, then somewhere else in the event there has to be that. And that increases baryon production in experimentally observable way. For instance, lambda is a baryon, K is a meson. They have the same strangeness content, but we can see that if we just look at LEP, tunes to LEP, the baseline Pythia does not describe this ratio, but with this kind of junction reconnection, you get additional baryons. And you can then also see that there's some very big effects in heavy flavor, where you get factor 10 enhancements of the baryon-to-meson ratio for heavy flavors, so in charm and bottom at low PT. So you're really getting a lot of the charm quarks that you're creating fragmenting into baryons rather than mesons. This lambda to D ratio here, it's 0.5. It's half of them that are turning into baryons. So that's quite impressive, that actually with junctions you can describe those features qualitatively. So I don't know if we have discovered string junctions at the LHC yet, but I think it's exciting, and at least we understand some of the thinking, the phenomenology around this now. There's also strangeness enhancement, which you may have heard of, where the baseline Pythia would say that the string tension that we talked about, kappa, 1 GeV per Fermi, is a string theory. That's the only fundamental parameter there is, right? And so the strange quark mass, according to the Schwinger mechanism, divided by the string tension, is what gives us the fact that the strange quark is suppressed, that we don't get as many kaons as pions. And in Pythia, in the baseline Pythia modeling, that doesn't depend on how many tracks there is in an event. String tension is just whatever it is. So the K to pi ratio is constant, and so is all of these things are constant with the multiplicity in the event. And these are just states that are going up in strangeness. But the data tells a very different story. And again, you have a very simple model prediction that says this is universal. It doesn't depend on what's going on in the event. Flat line, all of these flat lines here, that's baseline Pythia. And you see that the data completely disagrees with that. So that's very interesting that we seem to be seeing that as the events become more and more active, there's also the higher and higher proportion of strange quarks in. And I have to end now, I think. But of course, we're thinking about what could be driving that. And one of the things that could be driving it is when you have all these strings that you're creating that are spanning the central region. This would be a fun plot to explain, but I don't think I have time. But if there's a lot of them, then there could be an interaction energy between these strings. Remember, the strings in QCD are not fundamental strings. They're not superstrings. They're sort of emergent things like that arise because of vortex lines or whatever, how we should think about them with supercurrents in the vacuum. So they are, a property of the medium that they are in vacuum normally at LEP. But here in PP collisions, if there are a lot of them close by to each other, they should interact, and that could increase the energy per unit length, which is what the tension measures. So if you could increase the effective tension of the strings, then you could create more strange quarks, and that might be a reason why we are seeing them. Or maybe the string picture is breaking down. As I said, if there's enough energy density, maybe you're creating something more like a quark-gluon plasma. We're trying to find that out now. There's lots of exciting model building going on. And what particles you have in their spectra can affect things like jet energy scale calibrations in the experiments, which is really cool. But I'll stop there, and thank you for listening to Soft QCD for 2 lectures and coming back today, which is really good. Thanks.